Hello, and welcome to part 2 of examples for chapter 17. I'm going to be doing problem 4 and problem 5. So if you haven't read these two, make sure you do so now before I begin. So a couple things I need to, I want to remind you of in case you forgot them, involving the sum of squares, mean square residual, and mean square error, or if you forgot how to calculate those in general. One of the facts about the sums of squares and how they combine is that the sum of square total is actually equal to the sum of squares residual plus the sum of squares error. So since I know 2 out of 3 of these, the sum of squares total and sum of squares residual, I'm going to use that to find the sum of squares error. Next up, I want to remind you that the mean square for the residual is actually calculated by doing the sum of squares residual divided by the number of predictors. And then the mean square error is calculated by doing the sum of squares error, that should have been an equal sign, sorry, sum of squares error divided by the sample size minus the number of predictors minus 1. So, question mark for funds. I'm going to be using these three formulas to calculate some values. So, I'm going to actually copy this down because I'm going to use those two directly, but for the first one I'm not going to be. So we're going to make a mental note here that the sum of squares error must be taking the total sum of squares, which is 2,198.92, and subtracting 1,500 to 1,552.55, and I calculated this ahead of time, and it was 646.36. There's that first one. And now I'm going to calculate these last two using some of the results from above. So this first one, I already know the sum of square residual, and it happens to be the 1,552.55. And then I need to know my number of predictors. So if we look up above, we're using 12 observations with 3 variables to predict y. So I have 3 of them, 3 predictors. So when you do that division, you get 517.517. And then for our last one, we have the sum of squares error, which we found earlier to be 646.36. Hold on, I have to pause this for a minute. Sorry about that. I had a tickle in my throat and I was about to cough, and you didn't need to hear that. Anyway, so I need to divide that by my number of observations minus my number of predictors minus 1. So I have 12 observations. This is also your sample size. It's the number of data pieces you're using. There's 12. I have 3 predictors, so 12 minus 3 totally gives you 9, and then I subtract 1 more, and I get 8. So if you divide that out, you get 80.7. Is it 759? I feel like it should be like 8080. I don't know why. It's 795. Whew, I'm just trying to transpose my numbers for fun. So that's the results you get there for those 3. And we're going to use those to calculate the F statistic. So the F statistic is just the ratio of your mean squares. Just quick reminder, that's your mean squares residual divided by mean square error, which I calculated up above to be 517.517 divided by 80.795. And when you do that, you get 6.0408. Sorry. Okay, so I've got all these results, and I need to use them to come up with a hypothesis test. So I need to state my null and my alternative hypothesis. So this is a test for the regression, other R word, regression model. So I'm testing the whole model. So when I'm looking at my null hypothesis here, I'm testing to see, are all of my slopes significant? So in other words, do I think that, insert symbol, where's my beta? Here's my beta. Beta 1 is 0. Oops. I'm just going to copy this. Let me use it a bunch. Beta 1 is the same as beta 2 is the same as beta 3, and they're all 0. They're doing nothing. Standard modus operandi is that none of my slopes mean anything. They all equal 0. You could also write this beta 1 equals 0, beta 2 equals 0, beta 3 equals 0. I think they're all nothing. And I have 1, 2, 3 because I have 3 variables up here. 1, 2, 3. All right. Now, my alternative is that not all of them look like this. At least one is significant. And you can say that either way. I'm fine with you actually typing that up. Or you can just write that, not all betas, this looks weird, equals 0. So at least one of them is doing something. One of them is significant. Okay. So next up, I need to calculate the p-value going with this. So I'm doing the F statistic, and I'm going to be using Minitab to calculate the p-value. So remember, this is a right-tailed test. I just need to use the F distribution. So it's important to know which distribution I'm doing. When it comes to F, it's important to know that it actually uses 2 degrees of freedom when calculating it. And it's always k, comma, n minus k minus 1. So it's the 2 calculations used in calculating it. So our F is actually called F3, comma 8. And I'm going to be using that distribution to calculate the p-value. So let's see how to do that. So we're going to go up to Graph, Probability Distribution Plot, Probability View, and we're going to hit OK. And then I don't want T, I want F. Where is F? You're hearing my bird right now. He's making lots of noise. And it's going to ask you for numerator and denominator. Look up here. Numerator was R. R was using K, so that's why that's the 3. And then denominator is, oh my gosh, that was coming from MSE, so this is mean square error. So the error was using n minus k minus 1, which was the 8. So there's that. And then I want to go over to shaded area. And I want to do x value, and I want to do a right tail, because remember, all F tests are right tail tests, and I'm going to put in the F statistic to figure out what's above it. 6.408. We're going to hit OK. Ooh, that's super tiny. So from using this distribution, we know that the probability that F is greater than 6.408 is going to be 0.1604. So there you go. Shh, be quiet, birdie. That's, oh my gosh, I missed a 0. Hey, that looks really significant. And now it's insignificant, or significant evidence against the null hypothesis. So you should look at this and be like, oh, well, that's a small p-value, so we can reject the null hypothesis. It appears that at least one of my betas must be contributing something. One of them must be helping contribute to predicting y. So that's how you do number 4. Let's move on to number 5. Okay, so the easiest way to compute r squared is to see how well of a job your residual did at predicting the total amount of some squares. So I'm just going to copy this and paste it down here to steal some of its thunder. Oh, well, that works really well. No. Okay, that worked not at all. Maybe I'll cut that part. Let's just undo a bunch. There we go. So what's r squared equal to? Well, it's the sum of squares regression, or because that's what the regression was able to account for, out of the total sum of squares. So how much did the regression account for out of the total? Which is exactly what r squared means. So that's not too shocking that that's how you calculate this. So to do that, you do the 1,552 divided 0.55 divided by the sum square total we had earlier. This was actually a value we could have calculated without doing any other work. So all that stuff I did in problem 4 doesn't really help you do the first part of problem 5, just so you're aware. Oop, that's supposed to be a 92. And if you do this, you get 0.70605. So I would probably say, about 70.6%, because usually we report r squared as a percent. So as far as adjusted r squared, this one has a much more complicated formula. And just in case you forgot it, here it is again. 1 minus r squared times the fraction. How do I want to do times? Let's do a star. I don't like the x because we use x as a variable now. The fraction n minus 1 divided by n minus k minus 1. So there's your degrees of freedom popping up again. So I really don't want to fill all of this in, to be honest. I calculated ahead of time. And if you do this, you get, where did I write this down? 59.6%. There we go. So when you do this calculation, you always get the decimal because, well, proportions, proportions, proportions. I actually prefer it to the percentages. And also be careful when you're calculating r square adjusted, use the decimal version of r squared, not the percentage. You'll get a nonsense answer if you try to do the other value, just so you know. So what do these values really tell you? Well, they tell you the percentage of variability in y explained by the regression model. Woohoo! All right. Oh, I love this question. So, the F test is equivalent to the R squared test. So, when you're asking if R squared is significant, that's the same as asking if F is significant. So, yes. Hold on. Let me write all that out. So, those of you who look at the answers that do that. I don't really give the answers. I just give out the sheet. That's smart of me. The p-value for the F test can be used to decide this, since the F test that we did in part 4 is equivalent to the R squared test. This is me cheating to get an R squared without screwing everything up. So this is able to tell us that yes, R squared is significantly different from 0. Clearly these two are related somehow. They are correlated somehow. Or, you know, some of the variability in y is explained by the regression model. So there you go. Okay, next up we're going to be calculating some slope significance values. So if you haven't looked at the formulas for this in a while, you might want to. We're going to be calculating some t-ratios. So just like any real z-score, this is just a matter of taking and that should be a lowercase t. Thanks for screwing that up, word. I'm going to be taking my value for each slope, subtracting 0 since I want to know if it's different from 0. That's treated as my truth value, and then dividing by its respective standard error. So for this first one, that's 2.374. Cool. And then I need to go up and grab the slope for this first one. So I actually think I'm going to grab the whole equation and just copy it down below so that I have it to work with for this question. So I'm just going to put it right here, which I should have done in the first place since they're so far apart now. So my first slope, my B1 slope is 0.34, 0.34. And if you calculate that ratio, you get 0.14 for that t-value. And then we're just going to repeat this exercise. So I'm going to be lazy and just copy this and paste it down a couple times. And of course it's going to do that. I love it. There we go. Okay, so for this one, I'm going to be using, for part B, we're going to be using the slope for B2, and the slope for B2 is negative 2.49. And when you do its standard error for this slope, they give that to you It's 0.628. And when you subtract and then do the division, you come up with negative 3.97. That's pretty far away from zero. That one makes me a little nervous. Okay. All right. Last but not leastly, let's do B3. So for B3, your slope that you're interested in is negative 0.137. Subtract from 0, and then I got to put in the standard deviation for B3, or slope number 3, and that's 0.140. That's pretty tiny, so I'm interested to see where this goes. Okay, and that one comes out as negative 0.98. That one's pretty close to 1, so that one's probably not going to be significant. This one's pretty close to 0 also, so we'll see how this goes. Oh, so I am willing to bet, not that this is all scientific, that B is going to be our only problem child. So we want to ask at this point, is there any of these that you would drop from the model? So what I need to do is I need to test these. So I need to come up with the probability for each of these t ratios. So I am going to need to do a new probability distribution plot using t and the degrees of freedom for sorry, the residual, or not residual, I keep saying residual, regression. So the t I'm going to be using here is t with the nk minus 1. Why does it do that? It's annoying to me. I'm sure I'm the only person who gets annoyed by it. So for us, we're going to be doing t8 as our degrees of freedom. Yep. So what I'm going to do is I'm going to calculate the probability that we get this or something not equal to it. So I'm going to do a two-tailed test for all of these, and we'll see how we be. So here we go. So we're going to go up to graph, probability distribution plot, view probability, hit OK. And now we want to change to the t. And my degrees of freedom here is going to be 8. And I want to go over to shaded area. I'm going to be putting in x values for this, and so I'm going to be using these t ratios, and I want to do both tails. So the first one I'm going to do is 0.14, which I'm very certain is going to give me nothing interesting. Yeah, that's huge. So you would add these two together and get something like at the 80% level. So clearly this one is significant. So there we go. There's a way. Update graph automatically. Okay. I was going to try a little trick I learned the other day, but it's not working, so we're good. So now I'm going to do the one for B, which is slope number 2. So still the same distribution, and now I'm going to be putting in negative 3.97. And what's cool about this, watch this. It picks up that this is the one on the negative end and does the positive one also. And this is so tiny. This one is definitely insignificant, or, you know, it's significantly different from 0. So it's going to be the one that's significant. I just said the wrong thing. This is the one that's not insignificant. Oy, oy, oy. I'm getting terrible. Okay. So graph, probability distribution plot. Let's use this last one. And now I want to put in negative 0.98. And this one's also small, so. There we go. That's pretty much above 0. So remember, the null hypotheses for these types of tests is, hey, I think this slope is nothing. I think it's 0. So when you reject your null hypothesis, that's a good thing. That means you're significant. We want rejection. So in looking at the values we just looked at, only T2 was far enough away to be significant and therefore reject null. So we would say that only T2, X2, T number 2, that works, okay, has a slope coefficient that is significantly different from 0. So the other variables can be dropped. All right, so I'm hoping you saw from this that there's a couple things going on with this model. Sorry, I'm coughing so much. It only does about 70% of the job. It looks pretty significant when you look at the F value. However, only one of them is pulling its weight. Only X2 is making this look significant. So you would actually get rid of those other two and then rerun this and see if significance remained. All right, so that's all there is for 17. I look forward to seeing you in 18. Peace out, Girl Scout.